Welcome to the new era of video creation with Baoziba. We will discuss the following. What are the key differences between supervised, unsupervised, and reinforcement learning? Can you provide real-world use cases for each of these techniques?
Here is our content. Machine learning, ML, can be broadly categorized into three main types: supervised learning, unsupervised learning, and reinforcement learning. These paradigms differ primarily in how they learn and the types of data they require. Supervised learning involves training a model using labeled data to predict an output for new inputs. Unsupervised learning finds patterns or relationships within data that isn't labeled. Reinforcement learning is based on interacting with an environment and learning through rewards and punishments. Understanding these paradigms helps choose the right model for different problem types in real-world applications, whether you're working with structured data or autonomous systems. In supervised learning, the model is trained on a labeled dataset, where each input is paired with the correct output target. The model learns to predict or classify new, unseen data by finding patterns in the labeled examples. For example, in regression, we predict continuous values, e.g., predicting house prices based on features like size and location. In classification, we categorize data, e.g., identifying whether an email is spam or not. Common supervised learning algorithms include linear regression, used for regression tasks, and decision trees, used for classification tasks, which work by mapping inputs to specific outputs based on historical data. Supervised learning has a wide range of applications in real-world scenarios. Medical diagnosis: it's used for classifying medical images, e.g., detecting tumors in X-rays, or predicting disease outcomes, e.g., predicting whether a patient will develop a specific condition based on their medical history. Fraud detection: supervised models can be trained on labeled transaction data, fraudulent or not, to detect fraudulent activities in banking and financial sectors. Customer churn prediction: by analyzing past customer behavior, companies can predict the likelihood of a customer leaving, allowing them to take action to retain that customer. Recommendation systems: supervised models help recommend products to users based on labeled data of previous purchases or ratings. Unsupervised learning differs from supervised learning in that it works with unlabeled data. The model tries to find hidden patterns, structures, or groupings in the data without prior knowledge of the correct outputs. A common task in unsupervised learning is clustering, where similar data points are grouped together, e.g., customer segmentation in marketing. Another common technique is dimensionality reduction, where large datasets are simplified by reducing the number of variables while preserving key information, e.g., principal component analysis, PCA. Unsupervised learning is powerful when dealing with vast amounts of unlabeled data, where finding patterns or simplifying data is key. Unsupervised learning has practical applications in various industries. Customer segmentation: clustering algorithms group customers based on purchasing behavior, which allows businesses to tailor marketing strategies and improve product offerings. Anomaly detection: this is commonly used in security to identify unusual patterns that could indicate fraud or a system breach. Market basket analysis: unsupervised learning helps identify which products are frequently bought together, assisting in inventory management and product recommendations. Data pre-processing: dimensionality reduction techniques like PCA are used to reduce the number of features in large datasets, making it easier to build predictive models while retaining essential information. Reinforcement learning, RL, is a different paradigm where an agent learns to interact with an environment to maximize some notion of cumulative reward. Instead of being trained on labeled data, the agent receives feedback through rewards or penalties based on its actions. In RL, the agent doesn't know the correct action at the start but learns through trial and error. Techniques like Q-learning, deep Q networks, DQN, and policy gradients are popular methods in RL for learning optimal actions and policies. Reinforcement learning is highly effective in applications where a clear reward system exists, and the task involves sequential decision-making. Reinforcement learning has been used in several groundbreaking applications. Game playing. One of the most famous RL applications is AlphaGo, where the agent learned to play the game of Go by interacting with itself. RL has also been used in chess and video games like Dota 2, where agents can train by playing against themselves. Autonomous vehicles. Self-driving cars use RL to make real-time decisions such as turning, stopping, or avoiding obstacles by continuously learning from their interactions with the environment. Robotics. Robots use RL to learn complex tasks like picking up objects, opening doors, or even walking, by interacting with their environment and learning from success or failure. Personal assistants. RL agents can learn optimal responses by interacting with users, improving the quality of virtual assistants over time. Here's a comparison of the three learning paradigms. Data requirements. Supervised learning requires labeled data, unsupervised learning requires unlabeled data, and reinforcement learning needs an environment to interact with. Learning process. Supervised learning focuses on prediction, unsupervised learning aims at pattern discovery, while reinforcement learning optimizes actions to maximize cumulative rewards. Output. In supervised learning, the output is a prediction or classification. In unsupervised learning, it's clusters or reduced dimensions. In reinforcement learning, it's optimized policies for taking actions. Complexity. Reinforcement learning is generally the most complex due to the need for ongoing interactions and feedback. Hybrid approaches combine different learning paradigms to leverage their strengths. For instance, some systems use reinforcement learning for exploration, trying new actions, and supervised learning for exploitation, using known data to make decisions. Hybrid methods can lead to better performance and more efficient learning. For example, semi-supervised learning uses a small amount of labeled data with a large amount of unlabeled data, while self-supervised learning creates labels from the data itself, enabling models to learn without traditional supervision. In conclusion, the choice of learning paradigm depends on the problem at hand. Supervised learning is ideal when you have labeled data and need to predict or classify data. Unsupervised learning works well when you need to find patterns or reduce dimensions without labeled data. Reinforcement learning excels in scenarios where an agent needs to learn through interaction, like robotics or game playing. Understanding the strengths and limitations of each type allows you to make informed decisions about which algorithm is best suited for specific real-world problems.